Today we're going to talk about depth and data. Maybe I'll introduce myself first. My name is Jonito Arts-Argüelles. I'm an artist and a researcher at the Centrum Leo Apostel, CLEA in Brussels, where I'm just started my PhD. It's an interdisciplinary research group where we try to bring together as many disciplines as we can. Together with the curatorial studies here today, we're trying to start a conversation between disciplines, between arts and between science, but also between people. And in that sense, we invited two speakers today. One of them is going to do this via presentation, which is Liam Gillick. Liam Gillick is an artist based in New York. His work exposes the dysfunctional aspects of a modernist legacy in terms of abstraction and architecture when framed within a globalized neoliberal consensus and extends into structural rethinking of the exhibition as a form. Now, his presentation, before we start, comes with a statement by him that I will read to you first. This presentation is an Apple Keynote version of the film Margin Time, set to a soundtrack produced by the artist in the 1990s that can be understood as a hacker lament. Drawing on Catherine Malibu's ideas about plasticity of the brain, it is a science fiction film shot from the artist's apartment in New York City. The film shows the various journeys taken by a super-conscious agent between three different zones, each represented by iconic modernist architecture visible from the building. Shot during the lead-up to the artist's work for the German Pavilion at the Venice Biennale in 2009, the film considers three specific sites of power in a form that deconstructs specific approaches from developed science fiction in the 1960s and 1970s, specifically the writings of Stanislaw Lem and Christopher Priest. While thinking of what to produce for the German Pavilion, the artist considered the production of a science fiction film to create a working habit. He woke up early every day to film workers arriving to construct a temporary building on the site of the Sculpture Garden at the United Nations headquarters in New York. This temporary building now houses the offices of the United Nations, while the original Wallace Harrison-led complex by Niemeyer and Corbusier is undergoing complete interior renovation. The film also takes in the adjacent Roosevelt Island master plan for middle-class modern housing and shopping arcades by Philip Johnson, and the recently completed F.D. Roosevelt monument by Louis Kahn at the tip of the Roosevelt Island that points past the UN complex itself. The link between these three sites is made by a cable car shuttle. The film is a narrated series of shots that develops a revised language that reconsiders representations of power, memorial, connections, renovations, and the temporary displacement of bureaucracy. The erasure of the United Nations gardens, with its sculptures donated by various countries, all exemplifying particular projections of ideology from the depiction of an Irish famine boat to a thrusting young Stalinist pioneer, sits as an important absence within the film. The narration slips between historical references to aspects as varied as Louis Kahn's tragic death in the toilets of Penn Station, to the now completely erased original interior of the United Nations via a story of continual displacement and anxiety that forms the core of the science fiction story.
What's outside the universe? My friend Melody asked me this question when I was 8 years old. I usually had good answers for science questions. I was kind of a library guy. But this time, I had no idea what to say. The question was scary. I grew up in southern Utah, in the western part of the United States, and this is the home of red rocks, hot, dry summer nights, clear skies, and these are perfect conditions for stargazing. And as a kid, Melody and I would often bicycle out of town, stare up at the night sky, and ask each other questions about the cosmos. How big is the Earth? What is the sun made of? Why can't I see a black hole? How far away is that galaxy there? What's at the edge of the universe? When she asked me that one, I stopped and I thought about it, and I finally said, I don't know. And Melody said, my ancestors thought that the Earth was a big flat rock with a solid dome of sky above it with stars painted on it. It was all held in the hand of a gigantic creature who would occasionally shake it. And we stared up at the dome of stars, and eventually I said, well, they didn't have telescopes back then, so I think that sounds like a good first guess. But now that we know that the universe is huge, I don't know what's at the edge of the universe. Melody was an indigenous Native American from a local tribe. I don't remember if she was Paiute or Navajo, and the other kids would sometimes make fun of Melody, calling her nasty names. She didn't like homework assignments, she didn't like tests, but she ran circles around the other kids in classroom discussions with the teacher, and there was a reason why she and I were friends, because Melody was never afraid to ask the big questions. And when she finally asked me, what's outside the universe? The question caught me off guard. Well, nothing. The universe is everything, so it doesn't make any sense to ask what's outside of everything. Everything is everything. Yeah, but if the universe has an edge, there must be something beyond the edge, she reasoned. And we stared at the sky for a long time. And eventually I said, maybe there is no edge and no outside. And Melody said, yeah, maybe the universe just goes on forever and ever and ever, and that's all there is. And after another very long, cold pause, I finally said, everything is terrifying. And as you can see, I was a very serious child. Maybe not so completely serious, because to me, terrifying doesn't actually have to be a bad thing. But before we go too far, we need to answer a very, very important question. What is the universe? Picture the last time you were out in the wilderness and you looked up at the night sky. Thousands of pinpoints of light, photons traveling from stars and galaxies thousands of light years away, a light year being the distance that light travels in 1 year, to finally reach the earth and smack into your retinas. When you look up at the night sky, you're looking backward in time. But look closer. In between those points of light, what do you see? It looks like empty space, but it's not. Your eyes are pretty good photon detectors for one particular type of photon. But on cosmic scales, your eyes are terrible experimental apparatuses because they can only see a certain very narrow range of possible photon wavelengths. And there's so much more smacking into the earth than what we can see with our eyes. If you were to use humanity's best photon detectors, like satellite telescopes, you would see hidden light, photons from millions and billions of light years away, and eventually you'd see something absolutely remarkable: the cosmic microwave background radiation, light from when the universe was only a few 100,000 years old. This is the closest we can get to a baby picture of our universe. But wait a minute. Baby picture? A few 100,000 years old, that's a pretty old baby. Where's the light from before that? That light hasn't had time to reach us yet, and most of it never will. The universe is expanding. All of those galaxies you see up in the sky, they're all moving away from each other in all directions. The universe is expanding, but expanding into what? Nothing. Space itself, the background spatial metric grid upon which everything rests, is being stretched. 2 galaxies in our universe are like 2 pins stuck into a rubber sheet that is being pulled from all directions. From the perspective of an ant on the sheet, nothing happened to make the pins move. Space itself the background spatial metric grid is being stretched, and the distance between them is increasing. But it's not just the fact that our universe is expanding that is important. It's the particular way that it did so throughout history. There's so much that we can't explain if the universe expanded at a constant rate through its entire history. Why are there big things in the universe at all, like galaxies and big cosmic structures? Why does the stuff in that part of the sky look more or less like the stuff in that part of the sky? Why does that cosmic microwave background radiation, this baby picture of the universe, essentially uniform in temperature? Don't let the color coding fool you. My astronomer colleagues put that in to show the gradation. It's basically constant everywhere. None of this stuff makes any sense unless, right at the moment of the universe's expansion, it didn't just expand at a constant rate, but instead insanely inflated before then tapering off to a much more gradual rate. And this insane inflation of the fabric of space right at the moment of the Big Bang, this was not some minor thing. Imagine if you and I right here took a horse and we magically inflated it to the size of the observable universe now in 10 to the minus 32 seconds. That's what inflation was like at the moment of the Big Bang. This inflation was much faster than the speed of light. Most of the stuff in the universe was instantly separated from us forever. Because you know, the fastest possible way that anything can move, any information, any stuff can move in the universe is light speed. And if the fabric of space is moving faster than that for a certain period of time, certain parts of the universe will be separated from us forever. Thus, we are left with a new concept. The observable universe is a volume of space defined by all of the stuff that could ever possibly send us a signal that could get to us. And this volume must be a tiny subset of the entire universe, within which there's almost a very large number of other observable universes for other observers. And it gets worse. If you look closely at the mathematics behind this insane inflation of the fabric of space, it should go on forever, infinitely. But in our universe, it didn't. It tapered off and has been going at a much smaller rate for a long time. This must mean that our universe and the fabric of space upon which it sits can be thought of as two distinct things, because in our universe, inflation tapered off, but for the rest of the universe, for the rest of space-time, it inflated forever. And it inflated not forever, but infinitely, infinite expansion forever and ever. And as you know, with infinity, if something happens once, it happens again and again and again. If our understanding of inflation is correct, there must be an almost infinite number of other universes just like ours. In most of them, probably inflation never stopped, and they're completely empty voids. Nothing ever happened there. Everything's completely boring. But if our understanding, but with infinity, some of these other universes must be like ours. In one of them, one of you wore different shoes here today. In another one, coffee is pink. And in another one, an Earth-like planet was obliterated by an asteroid just as protozoans were starting to evolve. If our understanding of inflation is correct, then this isn't just idle speculation, but is required by infinity. However, I see the looks on some of your faces, and you're absolutely, completely right to be skeptical of this, because it's totally circumstantial. There's no evidence for this right now. You should be yelling at me. You're a physicist, man. We should have, you need hard evidence for this. And you're right. Why should you take seriously this circumstantial evidence? It's because it's not the only piece of circumstantial evidence that we have. Our universe seems to be filled with magic numbers, constants of nature that we measure, but we have no particular explanation for why their values the way they are. And if their values were to be slightly different, our universe would be a very, very different place. For example, in 2012, my colleagues and I, some of whom are in this room, announced the discovery of something called the Higgs boson particle. And the Higgs boson is a very, very weird and important particle. A reminder, the Large Hadron Collider is a 27-kilometer circular tunnel on the border of France and Switzerland. And to give you some comparison, this is what it would look like around Ghent. If you'd like to lobby for a very, very efficient subway system, then this might be a good way to go. It's a 27-kilometer tunnel on the border of France and Switzerland, 100 meters underground, and in this tunnel we use superconducting magnets colder than outer space to accelerate protons to almost the speed of light. And we slam them into each other millions of times per second, briefly recreating the conditions of the universe as they were just a fraction of a second after the Big Bang, 13.8 billion years ago. And we collect a record of the debris coming from these collisions, and we collect this data and we sift through it to look for evidence of new undiscovered particles that could help explain the most important open questions of physics. And back in 2012, when we announced the discovery of the Higgs boson, it was a fantastic discovery. There was champagne and celebration, and 2 white males won a Nobel Prize. What else is new? And it was a wonderful discovery for all of science. But there was a lot of head scratching, too. Because actually, from one perspective, we shouldn't have found this particle at all. The largeness of experiments like the Large Hadron Collider is important because the larger your experiment, the higher you can get in energy, in collision energy. And the higher you get in collision energy, it allows you to possibly discover new particles with very high mass m. This is due to Einstein's famous equation, E equals mc squared. M is the part that nature controls. It's just the mass of a particle. But E is the part that we can control as humans if we work hard enough. And if you if you build a larger detector, or a larger collider, then you get up to the possible discovery of a particle with a very high mass m. And the weird part about the Higgs boson is that there's nothing really in our theory to prevent the Higgs boson mass, this m, from being way over here, well outside of the range of the Large Hadron Collider. But we found it right down here. That doesn't make a lot of sense unless there were extra particles right around the corner where this Higgs boson would live. If there were extra particles just hanging around, just around the same place as the Higgs boson, this would be a very, very nice, elegant explanation as to why we would observe the Higgs boson right where we did. We do not see these particles at the Large Hadron Collider. I mentioned that the Higgs boson is very, very important. Let's be clear, it's absolutely vital. The Higgs boson is proof positive that something called the Higgs field exists. And the Higgs field is essentially a completely invisible jelly that permeates all of space everywhere. And if you're a particle with a mass, you are dragged by this jelly just slightly, and a little bit of your energy is stuck into a point that we measure as mass. And this is a good thing, because if the Higgs field did not exist, an electron would have a zero mass. And if an electron had a zero mass, atoms would never have formed in the early universe, and you and I would not be here to have this discussion. So it's good that the Higgs field exists. But what's keeping the Higgs boson all the way over here? Maybe it's just luck, but a very special type of luck. Our universe, well, nature loves statistical distributions. If you ever hear a nerdier statement in your life, I want you to tell me and I will fight that person. Nature loves statistical distributions. The average resting heart rate of adults will be distributed as a Gaussian distribution, a normal distribution. If you stand on a street corner, the rate with which cars will pass you is some kind of Poisson distribution. So nature loves statistical distributions. In fact, statistics and math, from one perspective, they transcend our universe. So what if our Higgs boson mass is just one of an almost infinite number of possible Higgs boson masses in a multiverse? In our universe, the Higgs boson mass was just right to allow atoms to form and for everything to evolve and for us to be here today. And in most of the other universes, the value was something totally different, and those universes are completely empty voids. The lack of extra particles at the Large Hadron Collider is not direct evidence of a multiverse, but it's another indirect hint that we should take this idea seriously. But again, I see the looks on your faces, and you're absolutely right to be skeptical of this. You should be absolutely skeptical, because at the end of the day, I'm an experimentalist. I need to design an experiment to demonstrate this proof positive, to show that other universes exist. How are we ever going to do that? We have some ideas, but I admit they're actually very, very difficult to pull off at the moment. So one way is you can look for a bruise on our universe. Remember those almost infinite number of other universes that were snapped into existence by the absurd inflation of the fabric of space? What if two of them expanded right next to each other and bumped against each other? Could that be what this little cold spot is on the cosmic microwave background? The jury is still out as to whether that explanation fits our data better than another one, but again, it's one more direction that we can go to investigate this type of concept. Another way is you can look for higher mass, big particles that will help explain everything, aka my day job. So just a few months ago at CERN, we announced the plans to build something called the Future Circular Collider, which would be 100 kilometers around and would reach energies almost 7 times what we can do at the Large Hadron Collider. This would open up amazing discovery potential because it's actually just okay if these extra particles that help regulate the Higgs mass, if they're just outside of the range of the LHC. That wouldn't be too bad. It would be okay. But what if we build this collider and we don't find those particles? Would I then be convinced that we live in a multiverse? No. We need to go even bigger. So the next generation, we would build a particle collider around the circumference of the moon. This would allow us to get up to tens of thousands of times the energy of the LHC. And if we didn't find the particles there, would that really convince me? Probably not, but let's think about this for a second. Imagine what we could do with a particle collider around the moon. The different things that you could, someone in this room or someone's uncle or cousin or niece would have to innovate to make this happen. I'm not going to go through all these, but we need lots of magnets. We need a space transport system. We need tunnel scouting and digging. We need new next generation particle detectors. We need all brand new data science methods that don't exist. We need a robust Earth to moon data communications system that's robust against solar flares and all that kind of a thing. We need all these different things. And I mentioned them all really, really quickly to just demonstrate to you that this is going to take a lot of innovation to happen. But even if we were to make that thing happen, would that satisfy me? It wouldn't. To really answer this question definitively, we would have to reach a very, very, very high energy scale. We would have to reach something called the Planck scale. And the Planck scale is such an unimaginably high energy scale that it's basically outside of the realm of possibility for our civilization to reach now. But it's the place at which everything would be revealed. It's the place where quantum mechanics and gravity, they must have something to do with each other. It's the place where we understand everything about the nature of time, probably. We would understand everything about gravity and about supersymmetry and about quantum black holes, all this sort of a thing. But by some very naive estimates, we would need a particle collider stretching around the outer edge of the solar system to reach the Planck scale. Clearly, we're going to need some major innovation to make this happen. But I mention these things only because, let me go back to this one. But even if we were to build the ultimate Hadron Collider, and we will someday, even if we were to build this, what will we do with the answers that we get from it? Even if we were to find overwhelming circumstantial evidence that we live in a multiverse, there's still really no way for me to ever contact another universe. Such a concept currently makes no sense. So are such questions meaningless? You may think so. And in fact, some scientists would agree with you. And in fact, some scientists are uber skeptical of our desire to even address questions like this with bigger machines, such as the Future Circular Collider. And they claim that such questions are non-scientific. But is that true? We started from known science, observations of the world around us, and we followed the chain of logic to arrive at the conclusion that we may live in a multiverse. It's a scary, startling conclusion, but it's clearly scientific. Just because we can't answer it today doesn't mean that we never will. Why do some people object to questions like this? Is it because they might be afraid of the answer? And is this the same fear that caused people to object to similar questions in the past, such as, is the Earth really at the center of the solar system? Or are the stars painted on a round dome just a few kilometers above our heads? The fear that you and I are not as special as we think we are. Perhaps more accurately, the fear that what you know right now is not all there is to know. Does this same fear affect you? What might happen if you quit your current day job or gig or whatever it is that you do and instead worked on that big thing that you've been thinking about for a long time, like starting your own brand new arts organization or a humanitarian organization or something like that? What might happen if you threw over everything that you have right now in your life and instead joined us working on the next generation of particle physics stuff, right? So all of the crazy crap that I'm talking about, building a particle collider around the solar system, it's all based upon current technology, which is decades old. There's research going on right now on something called plasma wake field technology, that if it works and it comes to maturity within a certain amount of time, it's possible for us to accelerate particles to higher energies and higher speeds in a much shorter distance. What if you joined this effort, some of the most brilliant minds, I don't even work on this, but some of the most brilliant minds in the world working on this type of a thing to help us explore the basic underpinnings of nature? What if, back to more quotidian things, what if, again, you kind of threw over what you're doing right now and instead worked on ways to solve poverty or to prevent governments from secretly surveilling their citizens? The answer to all these questions could possibly mean nothing, but you don't currently know that. And you never will unless you take the leap and find out. And to me, the terrifying joy of, to me, the safety of ignorance will never compete with the terrifying joy and the scary beauty of knowledge. We should always ask the big questions. We should always allow ourselves the bravery of stepping into the unknown, and we should always seek out new knowledge to vanquish the fear, because you know what? This fear, it distracts us from some of the basic truths of objective physical reality. At the end of the day, we don't need to be afraid of an almost infinite number of universes, because we know for a fact there is at least one universe. And you and I, when we as humans ask questions about our universe, you and I, humans, are the method by which the universe asks questions about itself. And when I see the government of the United States putting children into cages on the Mexico-US border, and when I see how otherwise very smart people are being tricked into voting for racist white nationalist candidates all over Europe and Asia and in India and Australia, and when I see that we've allowed decades of unfettered global capitalism to basically destroy the climate and we're not doing anything about it, and when I think about my friend Melody and how the other kids would mock and bully her, and how this made it difficult for her to go to class, and how she never went to high school, I feel anger. It's not just regular anger. I feel regular anger too, but as a physicist, I feel an extra layer of anger, because I see when we allow these things to happen, we're betraying a cosmic truth, that we're all parts of the same universe, and that we're all in this universe together. And so back on that rock, the red rock in southern Utah, as a child with Melody, I said, everything is terrifying. And after a long time, Melody looked at me, she said, yeah, but it would be scarier if I were out here by myself. And I looked at her and I said, yeah. And we stared up at the night sky, the stars and galaxies watching us from very far away. Thank you. you can see that at the end of that, a talk like that, there's built-in uncertainty, right? There's built-in like a little bit of a, because a lot of people, some people will think it's like, wait, what happened to melody? And then some people will say, wait, what about particle physics? How are you going to build the bigger machine? And somebody else is going to think, what happens to the universe? Because we do have this one universe that we know exists, or at least if you don't want to be some kind of solipsistic asshole or something, but we know that this universe exists. And the things that we're learning with particle physics, this type of research, it doesn't just allow us to, understand what dark matter is, which is a totally, completely, open question that is one of the most vital open questions of science. It doesn't just help us, look cool in front of our friends. It's like, hey, I just helped discover the Higgs boson, But what it does is it allows us to not just understand two of the main three philosophical questions in human existence, but the third one is still, I think of them this way. Particle physics is not so arcane because it's really, at the end of the day, trying to address some really basic questions that we all ask ourselves at some point, whether you're lying underneath the stars as a little kid, or if you are sitting on the toilet, or if you're like sitting on your bed at night thinking, what have I done with my life? You think to yourself, where did we come from? How does everything work around us? And where are we going? And the where are we going part is super fascinating, because what we're learning now about the continued expansion of space is leading us to some rather alarming conclusions about our universe. So the part in this that I mentioned is that I talked about the first so-called epoch of the universe's expansion. There was this insane inflation right at the moment of the Big Bang, and then it kind of tapered off. But it didn't go constant forever. For some reason, a few billion years ago, something else turned on to start this acceleration again, to start to speed up the expansion of space. So you can think of it like a little bit of a, it goes, and then it kind of goes small, and then like a few billion years ago, it started to expand a little bit more. And this is something we call dark energy. And we use that word dark because we have no friggin' clue what it is. But something happened to drive this accelerated expansion of the universe. And as even a few years ago, we weren't sure what that expansion, the current expansion, was going to do in the long term. And by long term, I mean, what is the eventual fate of our universe? What happens at the end? Is there an end? For a long time, we didn't know. It was entirely possible that the universe would do this expansion, and eventually it would start, gravity would win, and it would start to go like this again, and the universe would end in a big crunch. Seems somewhat poetic. You start with a big bang, you end with a big crunch. It was entirely possible until a few years ago. We now know pretty definitively that our universe will continue to accelerate and expand forever. It will go on forever and ever. And at some point, probably trillions of years in the future, everything in the universe will be expanding at such a rate that under this, say, magic assumption, if you were able to take the Earth and just assume that it exists in the same state with you on it, trillions of years in the future, the universe will be expanding at such a profound rate that there's no possible way for you to send a light signal to any other planet and vice versa, and for it to ever reach you. So the entire night sky would not be filled with stars and pinpoints of light, but would be absolutely, completely empty and black forever. But again, how do we know that? I've not traveled to trillions of years in the future to demonstrate that to you, right? Everything we say in science, every word that we put down in physics has some kind of uncertainty on it. And in astrophysics, there's huge uncertainties, right? I say trillions of years in the future. I don't know, it could be hundreds of trillions of years in the future. It could be a quadrillion years in the future. There's huge error bars there. But there's also error bars in everything that we do in physics, in particle physics. And this is one of the most precise and accurate experiments ever designed. We go to extreme lengths to make sure that our uncertainties are as small as possible. And so these uncertainties, though, sometimes people refer to them as errors. You know, you think of like if you've ever used like a graphing tool, it's like it has, you know, you can put like a histogram and it has error bars on it, and you call them error bars. Error, it's not, you know, it's equivalent to the concept of uncertainty, but it's not a mistake. Error doesn't mean you made a mistake. Error, uncertainty, is a built-in part of what any experiment needs to do. Your number makes no sense unless you give it an error bar. If you say that the mass of the Higgs boson is 125 blah blah blahs, doesn't mean anything until you put an uncertainty on what that number is. And that is built in not just to what experiments do, but it also is built into quantum mechanics itself. It's built into the fabric of what we do. So I don't know if I should go into any detail about this, but it's interesting to to look at an equation like this, because if you can find, what it's saying, you don't have to be a math person to understand this. What it shows is that x is position. It's like the position of something, like an electron, let's say. And the p is the momentum of this electron. It's not how fast it's moving, and it has a mass in there too. It doesn't matter. So you can think of it in terms of like its movement. What this equation, what this relationship tells you is that it's impossible for you to know with infinite precision both of these pieces of information at the same time. And that seems crazy, because if you zip in front of me on a wheelchair, I will know exactly where you are the whole time, and I will know exactly how fast you are going the whole time. This is not the case with an electron. If I know exactly where an electron is with high precision, I basically have no knowledge about its momentum. And if I know exactly how fast it's moving, I basically have no idea about where it is. This is built into one of the observations about the way that the most basic description of our physical reality, our physical world behaves. There are limits to our knowledge, built-in limits that are uncertainties that are impossible for us to get around. And that's sort of related to some of the things that Liam was getting at with his slideshow a little bit. Anyway, I'm not sure how long I should yammer about these things. I can keep going on, or if you wanted to move to like some questions or something like that.
Yeah. So now we move on to the question and answer part of this this evening. So if any of you have any questions for Dr. James Beacham, you can ask them. I don't know if any of you have any questions.
It's all completely clear. I hope so. That means I've done my job. Yes, absolutely. And there's no such thing as a bad question. I mean, I know that not everyone here is a physicist, so the completely basic questions are the best questions. Trust me, they're absolutely awesome. There's questions back there. Yes.
I found really nice that you touched the political questions and economical things like that. And my question is, do you have any idea on how to tackle that, or what's missing right now that we are gonna maybe have to do?
So you mean politics itself, the rise of far-right governments, or you're talking about climate change?
The reason we don't give people really opportunity to develop their knowledge, like the reasons why your friend didn't end up to really follow a career, to research her questions, or
yeah, I mean that part, I don't know. This in that case, it was anywhere you go within our contemporary sort of privileged white world, you're going to have that kind of built-in cultural, at least a little bit of that built-in socio-political and cultural biases, and like that'll be a breeding ground for people to make fun of people with different colored skin. But again, that to me is it's very much an accultured thing. It's very much a learned set of behaviors, and so it's not inevitable in any case, to my mind. But I don't know. I don't have a magic bullet for how to solve bullying. But I think that there's a parallel to be drawn between making sure that we have a society that values varying perspectives, that values differing perspectives, and making sure that that same society values pursuits that are based upon pure curiosity, right? And so I'm not just talking, of course, about particle physics, because it's true, the type of research that I do is, you're never going to make a product out of the Higgs boson. Well, okay, somebody, maybe, well, somebody, but, to my mind, it's not possible, because there are no Higgs bosons in this room. There's only one place for us to create them in our laboratory, which is at a Large Hadron Collider. You'll never hold a Higgs boson in your hand. It only lives for 10 to the minus 23 seconds before it then decays. So, but that's the thing we're really interested in. We can infer its existence because of the way the patterns that the way that it dies and these patterns that it leaves on our detectors, but we'll never see that thing itself. And that gap between what we're really interested in seeing and understanding and what we actually can see and what we present to the world, plots with lines on them and things like that, that gap is a built-in sort of, distance. It's a tension between the thing that we want to know and the things that we can possibly know. And in a sense, that's similar to, you can imagine that gap is present at a lot of the parts of science that are kind of the very edges of human knowledge right now. And that gap also, in principle, can lead to this kind of dismissal it's easier to paint people like me and people like particle physicists, some kind of like, elites that are kind of just making things up and not giving you the real answers. And that's partially why I don't really even like the concept of outreach. There's a lot of, in science, this is very often, it's like, oh yeah, you should do outreach. And that's, to me, that seems like it's like you're still, like this God on high giving information down to the plebeians. It's like, yes, I'm reaching out to you to give you my knowledge. And that's wrong to me. That's not the way it should be. And it ends up reinforcing these same kind of biases. And I think that the more urgent thing is that there's a similarity, to be honest, between the Higgs boson, stay with me for a second, the Higgs boson and climate change, for the following reasons. So the Higgs boson, like I said, you can never hold it in your hand. You'll never see it directly. There's no way for us to design a detector that could say, blip, a Higgs boson was right there. We can only see its effects. We can only see that it exists based upon lines on plots. And in a sense, climate change is the same way. You cannot experience personally climate change. You can experience weather changing, but that's not the same thing. The only thing, the climate change, the anthropogenic global warming is only available to see on plots that show the entire globe collectively warming up. And we know what the cause of that is, and we also know what the answer to it is going to be. Everyone around the globe has to act collectively, because it's not going to be an individual thing. You personally cannot solve climate change. And so, of course, it's a huge, symbol for somebody to say, I have a terrible carbon footprint. I fly all the time, right? I'm sure it would be a symbol if I were to say, yeah, I'm going to take trains more often. But that's not going to solve the issue. It's going to take a complete collective action for governments around the world. And so the thing that we can do there is that in a practical sense, you can refuse and you can fight any candidate that doesn't recognize the severity of the situation, and only advocate for representatives that do understand this. I feel like I went off piste there. So.
No, I think you covered exactly what we wanted to know. What I was interested in, and you kind of said that yourself, some people ask what happened to Melody. And I kind of wanted to know what happened to Melody.
I lost touch with her after like middle school. So we were friends when I was a little kid, and then how like paths start diverging, and it's like we were never not friends. But then as far as I remember, she got pregnant and then never went to, as a teenager, and she never, and it was southern Utah. There weren't very good support mechanisms for teenage mothers, and so I don't think she ever went. In a lot of Native American communities and like indigenous Native American communities, there's a high rates of domestic abuse and things like that. So it's I lost touch with her. I don't know where she is.
Too bad. My next question was, has she ever seen this presentation? Because that would have been interesting. Well, that kind of leads me to. So there's what I wanted to ask earlier was, there's this. You touched upon this a bit in your presentation. There's this kind of bias towards what science is, And I mean, we see this in the same way towards art. I mentioned to you earlier that there's this sort of idea when you talk about art to people who maybe don't come in contact with art a lot, or there's this 19th century kind of view on art where art is sort of like an aesthetic kind of thing, where art is just about beauty. And there's the same thing about science, where science is sort of like, you have an hypothesis, you make an experiment, and then you say it's right or wrong. But this is not how science is, and it's not how art is. How do you think that evolved, and how do you think those two, I mean, do you think those two sort of, is that the same kind of bias, you think, or is it something that, how can we combat that as a bias?
So, yeah, it's a really good question. I'm also, you know, interested to see what other people might think about that, because I mean, to me, it's totally true that the 20th century changed so many things about our understanding of culture, about progress. This notion of progress upended the Enlightenment era version of like, oh yeah, everything's just going smooth and it'll keep going in a linear fashion. But I think that what we see now is kind of, we're in a really weird time right now for both art and science, is that we're kind of, we've had this 20th century that saw so many upheavals, both in artistic expression, you know, like, I mean, abstract expressionism was radical for a reason, right? It upended, you know, centuries worth of kind of like this hegemonic attitude toward, you know, like really realistic paintings and things like that. But also the 20th century of science was filled with like almost like clockwork, amazing discoveries that just completely upended all of knowledge before that. I mean, it would have been great to be alive during the early 20th century as a scientist, because so many insane things happened. Like just to see these things happening in real time would have been great. Like, you know, kick off the 20th century with two gigantic bangs. You got 1905 and 1915, when Einstein separately totally and completely changed our basic understanding of the way physical reality works. That's amazing. And of course, he didn't do it alone. He was building upon knowledge from so many different people and drawing all these threads together. But then you had the development of quantum mechanics, which was another completely radical way of looking at the world. And then this ended up doing this kind of like this wonderful interplay between math and physics, and experiment through the 20th century led to this thing called the standard model of particle physics, which is the thing that we, you know, that we have right now. And it's capital S, capital M, and it earns that name because it's so good. It's so precise. It's like basically if you start with some rather rudimentary, okay, maybe not rudimentary, but rather simple math, straightforward math, and you kind of just turn the crank, it makes predictions as to what you should see in a particle physics experiment. And almost all the time, it's right there. It's passed all of the tests that we throw at it. It's one of the most successful achievements of humankind. But we also know for a fact that it's incomplete. We know that it's not wrong, but it's incomplete. There has to be stuff beyond this. And this happens in such a catastrophic way right now that it's like it almost hurts the brain to think about. We have two completely different, separate mathematical frameworks, one of which describes everything so well at the smallest possible level. Quantum mechanics, quantum field theory. It's so good. It's like right on. And we have another one called general relativity that describes everything in this cosmos really well. It's just so remarkable. Even like a couple of years ago, discovering things that were predicted by it back 100 years ago, gravitational waves. These were predicted 100 years ago, and then they showed up in an experiment just a few years ago. It keeps winning. And then you might think, yeah, but one coherent mathematical framework for all of objective reality has to be there. So let's just put these two mathematical frameworks together. If you do that, everything breaks. You get crazy, insane answers like infinite energies and insane. It makes no sense at all. It basically is telling you that you've done something wrong. So for the longest time, we have been trying to figure out ways to get those two things to go together. That's just one example. There's also things like dark matter. We know that dark matter exists, but we don't know what kind of particle it is and if it is a particle. So there's these things that we've had kind of on our plate to discover for decades, and we need answers to these things. And right now is such a weird critical juncture for science because we are definitely on the cusp of a revolution, but we don't have any idea of where this revolution is going to come from, because we have all these open questions of science, and we had a bunch of kind of, you know, directions and suggestions as to where we should go to find answers to these, and they're not panning out. I mentioned the lack of these extra particles. This is a framework called supersymmetry, We don't see any evidence of this at a Large Hadron Collider yet. For any physicists in the room, yes, we'll still be looking for 2 more decades for this stuff. And it's entirely possible it could show up not just like immediately out of the starting gate with a Large Hadron Collider. It's possible that it could only show up with a huge amount of data. It's a longer discussion, but yeah, we're open to this. It's definitely going to be part of the research we're doing there. But these are just 2 examples of things that, for the longest time, we sort of had hints as to where we should find these things. And the Higgs boson was like that too. The Higgs boson was predicted to exist, but it didn't tell us where we should find it. That's kind of the subtext of that one slide with, it's like there's nothing to prevent it from being over here, so why do we find it over there? But it turned out it was just there. And that was the last remaining prediction of this standard model. We have all these huge open questions, and we have no more flashlights. We have no more like kind of lampposts saying, yeah, look over there. There's definitely some kind of revolution coming, but I don't have any idea when it's going to happen. And it could be this cusp of revolution could be, I don't know, 100 years. I don't know if that answers the question at all. Yes. Yeah, well, I said that when I was 8 years old, right? That was a long time ago. And in fact, but that's actually really interesting too, because this relates to this notion that even in some of Liam's work, he talks about, he investigates the invisible, and he investigates hidden structures, and trying to somehow figure out how these affect us in different types of political ways. I think this is a really interesting slideshow, by the way. But that's another really key point, because that photo, that image that was produced by this collaboration, the one, of course, the orange donut right in the sky that everyone's seen, it went viral for a reason, because it's absolutely remarkable. I see that every time, and I'm just like, whoa, this is amazing. And it's an image of it's a kind of a souped up image of the gas, the hot gas that's around the edge of a black hole, but it's not a photo of a black hole. Such a thing makes no sense. You can't have a photo of a black hole. There's no way. But again, that's another version of that thing where there's this gap between the thing that at least I, as a scientist, desire. I want to hold a Higgs boson in my hand. I want to stand on a cosmic beach and feel a gravitational wave crash over me. I want these things, but I can't. It's impossible. Also, in that black hole photo, I want to see the middle. I want to see beyond the event horizon. But that's physically impossible to do. And there's that gap between the thing that we want, the thing that I intellectually desire, and the thing that I can possibly ever experience, that leads to some tension. And you can extrapolate this to other things in politics and society too. Other questions? Yes.
For me, it's like it appeared in several moments. The question about this one social outreach in the view of science in the society. I think it's very interesting, and it's also part of the problem with the Trump and why is that kind of backlash against science? Why is this kind of backlash against expertise? I think it's part of the problem is that science become like too distant. Maybe like this false image of objective, really technocratic science that this white guy as science, but it's also I think it's the way the science is communicated that people get this report, but the media go mad with that, but they don't understand this. The process that the science is kind of choosing different path and then trying, and it's there's more doubts. There's also the social aspect of the science, and it's why we do this research. It's the science as an actor in some social academic environment. It's much more complex picture of that. But on the other hand, people stop to understand what's going on because it's too much. It's every discipline has the breakthrough, 20th century. It's nobody could grasp what's happening. So it's a big problem. How to communicate science? How to use the science as a kind of a model for activity like art, the way you pursue as an actor in the social academic environment. How to change the way the science is deal with by the society, by the person in the society. Yeah.
It's true, and it's something that you know, if we want to just make kind of bald-faced one-to-one comparisons, is something that also happens in the art world, right? Kind of what you're intimating to. It's also related to the question that you asked that I didn't really answer, is that we have this constant, you know, stream of discoveries that happened through the 20th century in science, and that was great because it kind of just changed everything so many times, and it led so many of us to think, whoa, science is so amazing, and it really is. It's you know, it's the best way that our species has to, you know, the best set of tools to determine truth from falsehood in a reliable way. But it also kind of did a disservice in a way, because it makes people think that science is about making discoveries, when in fact it's not. It's about kind of going through fits and starts and saying, huh? And what, you know, as you know, science doesn't really progress by eureka, like a white male changing everything by themselves. It progresses through like, whoa, what does that mean? And then people think about it and they try to do other things and they see something weird. And my favorite art does the same thing, right? I mean, I don't care if, I honestly don't give a damn if George Condo says, it's like, okay, it's you know, it's 9 a.m. I'm going to make a painting, and then he stops at 12 and goes to lunch. You know, that's not that interesting to me. It's way more interesting if somebody wakes up and they're like, I can't get this image out of my head. I can't get this feeling out of my head, and they have to go through several different iterations, and they have to try it in different sculptures, and then it turns into this body of work. That's way more interesting to me, and that's the way that art, you know, I don't want to say progresses, but happens. That's the stuff that pops off the page or the stand or whatever to me. And but what we keep doing is we still have in our brains that, you know, we still hew to this notion again, these archetypes, these like things of the artist, or I'm sorry, the scientist is this, you know, white man in a lab coat, you know, changing everything by himself. And then we also have like the artist, you know, depending on who you're talking to, is, you know, or is like the, you know, Pablo Picasso, and like the brusque male, and, you know, just by channeling his bald genius, his rough genius, is doing everything himself, when in fact he was exploiting, you know, teenagers, and sexually harassing women. You know, this, I mean, this type of image needs to be torn down. This type of image needs to be broken down, and it's happening in smaller pieces in the art world and also in science right now. We have a huge, nice, we have a very good set of initiatives to try to make sure that our inclusivity and our diversity and our representation changes, but it's a huge uphill battle because of these built-in biases that we all have around us. And it's also in the art world. I mean, we were talking about this earlier. It's like just now people are seriously taking serious the concept. It's like, oh, by the way, Marcel Duchamp did not create the urinal thing. That in fact was Elsa von Freytag-Lorenhoven. Let's give her some credit instead, right? Finally, articles are being written about this in a serious way, rather than just kind of being the thing that somebody mentions and then they get painted as like the feminist asshole. It's like, oh yeah, you stop that. It's really this guy's thing. And this happened in smaller doses, but it's still, we have to fight against that all the time. And so, I don't know, one of the things that I think is most important is in both science and art is representation, right? In science, you know, in science outreach, right? And for example, right here, I mean, I'm happy to be here, but we should also have like a woman of color up here, a scientist, to be on this, you know, this discussion with us, right? Because that representation will then just go out into the world, and someone who's a little girl of color right now will say, oh, wait a minute. It's not even verbalized. It's like, that could be me, and then that immediately that barrier can be broken down. And it happens with art right now in the art world too. It's like you have at the same simultaneously you have such a bald-faced version of extremely wealthy, you know, people who have been exploiting the system for decades, and they're paying $91 million for this super goofy Jeff Koons sculpture, and at the same time you've got gigantic museums whose like permanent collections are still like 85% by white male artists, and they will have like they'll have one sort of you know, like a retrospective of some, you know, of some giving lip service to some, you know, female artist, but then they won't actually buy any of her artworks for their permanent collections. So this is an uphill battle that both disciplines face. This got really political. Yeah, go ahead.
Would you say that in a way you're invoking melody to frame your narrative? Wouldn't that be an absolute performance of that mastery of the other? And especially when questioned, what happened to her, you just basically use a statistic, that great slide you showed where everything is just a statistic. She's a blip on this. She's probably, Native American, and therefore probably some, domestic abuse situation, and therefore we could shove her. In fact, I don't know what she is, and I could look her up. So isn't that like, in itself, the absolute performance of that lip service that you just suggested? And maybe, that's not a critique, this presentation is fantastic, but it's more, how do we turn that lip service question to really rethinking these kind of epistemological groundwork that we're on, and just suggesting that Duchamp is maybe a woman or whatever, it's still basically, we're looking for these like source subjects, these sole source subjects to create histories that are indeed always these kind of linear graphs with the blips. Yes. And if we could just use melody, if we could even use someone, but just as a name, to really just undermine exactly even the question, not where is she, but how can even, let's say, to be simple, like a Native American non-blip on graph understanding of the world could undo everything that I've even performed tonight. And that would be the question that would go beyond the lip service that you just actually lip service.
Yeah. No, it's a valid criticism. I totally accept that. In fact, I thought through that very critically before I ever used any of my stories with her or some of my other friends as a kid. Because growing up in Utah you go back there as an adult and it's quite beautiful, but growing up there as a kid is horribly boring. You had to make up your own world. And so this is part of what I would do with my friends. We would just sit around and ask questions and be super curious. And Melody was one of my friends, and she was really awesome. And I did think about that critic. It's like, should I actually use her story the way I do? Am I just using it in the way that you're intimating? And I think it's a valid criticism to say that I am. To my mind, it does this thing that is what I was just saying now, which I feel a strong dedication to, which is shown representation. She's kind of the hero in my story. And so the story to me is allowing, or is like, it's designed explicitly to have the center of the story be the her rather than me. And that's the only thing I can do because I only have one me, right? I can't, I want to give the talk and I have to frame it somehow. It's a valid criticism, but I don't really know how to solve it otherwise. I don't really have a perfect idea. Rather than taking also my advice toward the end for myself, maybe I should stop doing what I do now, stop being a particle physics person, and instead start an organization devoted to science in say North American indigenous communities, something like that.
Maybe more exciting could be, you mentioned Pollock, for example, in painting, endless comparisons between two fields, which frankly doesn't seem that productive. But say you say, like action and Pollock, like it seems like if we as the art world can easily do without Pollock now. And those stories, let's say the art from say the late 30s to the 50s, doesn't need him anymore, doesn't need Clement Greenberg. So is there something like an equivalent in this decolonizing the history in science? Can we do it without Einstein, which keeps basically those points? Is there a way?
It's harder. In science, I have to admit that I have not found a way around it with some of the big names throughout scientific history. If you go back farther, you can point to some things that have been swept under the rug, people that have contributed to some of the old school guys like Leonardo and Newton and Galileo and these things like this. But through the 20th century, we have lots and lots of notes, and we have lots and lots of records from these things. And it really was, I don't think that Einstein necessarily was by himself did everything, but and I mentioned this too, but he was definitely in the right place at the right time to take all these threads and put them into the right direction, and it's kind of unavoidable. And I think that in that case, it's in the history of science, especially 20th century science, in physics at least, there are the known examples where women's contributions, for example, did get swept under the rug and marginalized. And those right now, there's a huge push, and very, very good push, to make sure that they're back on the radar of people like Rosalind Franklin, people like Vera Rubin, people like, at the time that had the discovery they made was totally marginalized in favor of the white men that happen to be on the team as well. But that's being shifted right now. But for certain things, it's simply impossible to get away from in science. What I do think we can do in science, though, is we can recognize the way to decolonize science that's a little bit better, that's more manageable, is not to try to deny the legitimate practical history of 20th century science, but instead to recognize what is built into the society that, the unconscious biases that were, and cultural biases that were built into the society that made it so that only people like Einstein at the time happened to be around. Because it's not, I'm not one of these people that thinks that Einstein totally was inevitable and he was absolutely like, he had to come and he had to be the genius to do those things. If we instead had a different society that was not built upon, exploitation of African nations to own their bodies for, to make cotton or to pick, and if it was not dedicated to the explicit, the denial of the voices of people of color, we probably would have had somebody else that would have put all these threads together, or maybe multiple people to put all these threads together. So the critique to me the decolonization has to be to go back to the basic, the underlying sort of biases within society that led to the situation where only somebody like Einstein could have been in the right place at the right time in a very privileged way, and also somebody like me, right? I'm horribly lucky because I was born in the right place at the right time, to have parents that encouraged my love of art and literature and also science and curiosity. A lot of kids are not so lucky, and they never would have been. So to me, we have to interrogate the underlying causes of these things rather than just trying to ferret out a different narrative that says that Einstein did not actually do what he did. He did. He totally did. But he also, of course, didn't do it alone. And we also need to think critically about why we still tell the narratives about who gets to do science and who is allowed to shine in science. Because we also have a similar situation where there's a reason why, back to one of the other questions earlier, there's a reason why it's totally valid that people in communities of color might not be so happy when they hear the word science, right? There's a reason why why science as a concept, it deserves our interrogation, it deserves our critique. Because, for example, if you're a black man in the United States and your family, you had an uncle or a grandpa who was part of the Tuskegee syphilis experiment, maybe you don't think science is such a good thing. Maybe you don't have a good association with that. If you happen to be, somebody who, whose grandfather was vaporized in Hiroshima and Nagasaki, maybe science is not the most important. It's not like the lofty ideal thing that everyone else on TV says that it should be. So we also need to keep this stuff in mind, that all of this stuff is part of the rich tapestry of bigotry that's behind all of the society that we live in. I have no idea if that answers your question, but it's a longer discussion. I think your points are totally valid, and it's something that I struggle with every day. I don't have the magic answers for these things.
Totally different question. I liked your idea about the universe looking or talking at itself through beings. I like that maybe think of, because there was a book by David George, The Fundamental Reality, maybe think of his theory, which is a lot of, I don't know. And then that was my question. It's also a theory about the multiverse. How do you relate to he's writing? He goes really far. Yeah. This quantum computing and VR.
So the concept is that statement that I make in the talk, it comes from, for me, it comes from it was a very personal thing again for me. My whole talk is very personal, but it's because I read a book by John Wheeler when I was a little kid. And John Wheeler is a really great physicist, did a lot of fundamental, stuff in gravitation and stuff. But he wrote it, he also thought, he was one of these people that thought critically about the underpinnings of science and thought about like kind of the more epistemological and ontological issues that go on when we codify these things into this set of tools known as science. And I remember flipping through one of his books at one point, and I came across this diagram that was so bizarre, and it totally gripped me, and it's been haunting me like my whole life, which is, I don't have the slide here, but it's basically, if you imagine a kind of a Latin character U, for a universe, right? And it starts over the right side, really thin, and then it gets, as it goes to the other, it goes down and then comes up the other side, it gets thicker and thicker. And at the very end, on the very top, on the left part, there's an eyeball that is then pointed back toward the first part of the U, and there's a little dotted line going over there. And I saw this as a little kid, and I'm like, what is that? And I read his ideas about like this notion that the universe, you know, because you kind of at some point, if you ask these same questions about the cosmos around you, and you're this curious little kid, you get to the point where you're also asking, is the universe inevitable? Is it inevitable that we would come up with the universe that we have, or is it not? Are there other options? And does the universe only exist because we observe it? Does the universe only exist because we allow it into our consciousness? But then our consciousness is a part of the universe. So he's pointing out this kind of model of the universe as being one example of an existence, of an expanding physical existence that had to get to about apparently 13.8 billion years old to eventually evolve at least one species that has some type of consciousness that allows it to be self-reflexive. And you know, anytime somebody tells you, so I didn't see the performance about the Drake equation, but the Drake equation is a good example. It's like, it's really fascinating, but there's a lot of assumptions built into that thing, right? And so it's really hard for us to put any kind of really reliable, objective kind of probability on whether or not other creatures exist. But you then ask the question: Is our universe really just an example of one possible universe setup that apparently you need about 13.8 billion years to evolve at least one species that can then be self-reflective and start asking questions about the universe? And that diagram has haunted me for my whole life. I don't have the correct answer to it. But again, most of these things, and I'm in the talk, for example, it almost seems like I'm dismissing the attitudes of some scientists who's like, yeah, that's non-scientific. It's not, it's outside of the realm of what science does. It's philosophy, if you want, or poetry, if you want to talk about it. I'm not trying to be dismissive of those ideas. What I'm trying to say is that when we have an overwhelming dearth of circumstantial evidence, that no scientist worth their salt would say that is actually a demonstration of the thing. But again, we should not discount circumstantial evidence. We should not throw that away and say that this is not something worth thinking about, because at some point somebody's going to come up with a way possibly to test it. Again, right now, I have no idea how to define that. Just to be very clear, I have no clue how we would ever directly, right now, I have no mechanism that I can propose you right now, how we could ever directly detect and interact with or exchange information with another universe. That currently makes no sense. But, in the future, this might change.
Does that answer your question? Well, I quickly wanted to come back. This is 2 questions before, but I wanted to say something about that, about the fact that science and art, which you answered correctly, it's hard for people to understand sometimes, and it was hard for. The question was, how do we make it more interesting for people? Because a lot of what, and I guess this also relates to climate change in a way. A lot of what scientists try to do, or when we publish things, or when we talk about things, is we use facts and we try to explain everything really carefully, but that's not always very flashy. And I think, or at least for me, one of the issues in the last 10 years, I think, is that flashiness has become important. Things have to be bite-sized. Things have to be interesting, directly, immediately. And that's just not how science works, or that's just not how an actual explanation of anything works. And I don't know if there's any way around that. The question was, what would be a way around that? But I don't know if there is one. Because, I mean, that would be to dumb it down to a level then why even say something about it? I don't know if you have any other thoughts about that, but...
So I'm a full-time researcher, a full-time physicist with Atlas, and this is kind of like my hobby, just because I think for reasons that you intimated, I think it's important, at least it's important to me to investigate ways of connecting. I wouldn't even necessarily use, like I said, I don't like the word outreach, but I would not would not like to use the word science communication. Also, it's almost as though what I really want to do is I want to connect with people. I want to connect with them in some way that's important for them. It's like, because they still have this, this overarching, suspicion that every human still secretly down deep inside has a curious little kid inside them. Because if you're a little kid and you're still below some age range where society starts to impose the kind of unconscious biases and the values on you, you still will look at like a crumb of bread and you'll start to cut it up and you'll think about how small could I go, And then if you look at the night sky or the evening sky and you think, why is that part blue but that part is orange, And that desire to know something that you currently don't know is, again, it's a gap between. It's a gap. It's a chasm between your current understanding of something and some observation that you make, and that's really where curiosity comes in. That's where it's a way that you can define curiosity, is this desire to bridge that gap between the current way that you quote unquote know how things work and some observation that you make that doesn't match up with that. And that for me kind of guides what curiosity is in science. It also sort of guides what curiosity is in the arts as well. And again, I totally agree that sometimes these discussions, they end up just being sort of superficial in a way. But there's a lot of superficialities that you can kind of dance around and hopefully get to some meat at the end of the day. But what was the question again? Yes. So yeah. It's important for me because it's my hobby, and I want to connect with somebody that I want to understand. I want to figure out what it is that they need to understand why the type of research that I do at all. Why is it there are thousands of people come to CERN to do this? Because none of us, we're not going to get rich. We're not going to make a product out of this Higgs boson. We're not going to, become famous or anything, because, even with a Nobel Prize, right? I'm one of these people that thinks we should abolish the Nobel Prize because it's a relic of the past, where it was this idea that a lone person can change everything by themselves, which does a disservice to the way science really works. And clearly it's a horribly flawed instrument, because only 3 women in the history of the Nobel Prize have won the physics Nobel Prize. Clearly it's bad, but it still reinforces these same biases and prejudices that we have. But the part is, if I give a public talk and the only thing that someone comes away from it with is the numerical median value of the measured Higgs boson mass, it means I've failed. But if instead they come away with some kind of sense as to why thousands of us would come to do this type of research, then that means that maybe I've helped understand, I've kind of connected with what their kind of deep down inside curiosity still is. And I think, that to me is just an interesting way to do things. But anytime you have to do that, yeah, eventually you do have to use, I don't want to say dumb it down, but you have to use heuristics. And heuristics to a certain extent are always going to suck. And so it's, as for somebody that talks to the public about science, for someone who talks to non-specialists about science, you end up, it's a constant sort of battle of frustration, internal frustration, where you're like, should I really say this sentence? It really doesn't do justice to the thing I'm trying to say. Okay, fine, I'll say it. And you have to cut it off at some point. Otherwise, the only thing I can say, and be honest. Otherwise, the only honest thing I could say is that all of you need to stop what you're doing and enter a graduate program in particle physics and take 6 years of quantum field theory calculations, because that's the only way you're going to understand it. Because that's not really true, right? Because that's the only way you're really going to go through the whole process to then become a specialist in that area. To really get a sense of why we do what we do, you don't need all of that. You can get a sense, and you can get an understanding of why we're drawn to these questions without going down the road of 6 years of quantum field theory calculations. So I don't have a way. I don't know if there is a way necessarily to do science communication or science connection or engagement or something in a different way that would avoid having to use heuristics. You always have to use heuristics, because otherwise I'm just going to put a bunch of Feynman diagrams up here and do the calculation in front of you and just wait for applause, and that's never going to happen. But it's also it's interesting with this particular context as well, because speaking of superficialities between art and science, right? One of the things that always frustrates me is when people coming to an quote-unquote art science event, they're sort of in this notion of, it's like, oh yeah, the art and science collaborations, that's, oh yeah, so you hired an artist to come and design a better diagram for you, right? It's like, no, that's not at all what I'm talking about. But that's not to say that's a bad thing, because yeah, some of our diagrams are probably crappy. We could probably hire an illustrator to help us. But that's not the same thing as an art-science collaboration that means anything to me. And so you can kind of think of it in two different directions, right? You can think about what can art do for science, and in that sense, it's like almost what can design do for science? In the sense, how can they help us? How can a designer help us present our information better so that it's more understandable? How could a designer or an illustrator help us with our animations? I spoke at a design conference in Moscow a few weeks ago, and some guy afterwards, he's like, "Oh, that was really, really good. But my whole design team, we're really good with like animations, and we kind of laughed at your animation there. So here's my card, and if you want to really soup up your animations, let me know." And that's great, right? I mean, that's awesome. But it's not really what we're talking about when we talk about an art-science collaboration. So the thing that I'm more interested in is almost like, what can science do for art? Because one of the fascinating things with the Large Hadron Collider is that it's this gigantic experiment, like the largest experiment in human history, and it has thousands of people from all around the world working on it, and it's got a pretty decent budget. Trust me, the budget is actually not that large in the larger scheme of things. If anyone ever tells you this is a waste of money, they're crazy, and I'll tell you why if you'd like. But it's a huge endeavor, and there's so many people coming to work on this, and you're like, at the end of the day, what we produce are these papers that have words and plots in them. That's what we produce. Maybe some of these event displays that have the kind of cool arcs coming out of them, and those are nice to look at. Maybe we need an illustrator to help us, do those better. But that's just one example of a human filter in between the thing we're really interested in knowing, which is what happened right at the moment of the proton collision, and what we then present to the world, which is this paper with plots and words in it. The filter in between that is a human known as a scientist, a particle physicist. What if we took that filter out and put a different filter in? What if instead we put in, like, I don't know, Gerhard Richter? or what would Richard Serra do with two white males? What would some other filter do with the thing we're really interested in knowing something about, which is right down at the very core? And then what comes out, and then the filter is another person, is another human being that's not a scientist. What might that be? And it's almost like a superficial version. Am I really saying that we should get Gerhard Richter and allow him to like fiddle around with the proton beam inside the LHC? No. But what I mean is that these are the collaborations that are really interesting to me, where you get a scientist and an artist who have thought very critically about, to my mind, the kind of invisible structures around us all the time, the structures that coerce and oppress us socially and politically, and then the scientific structures, the ones that control everything around us, quantum field theory. Are there other forces of nature? What is dark matter? You all have about 1 billion particles of dark matter coursing through your body every second. What is it? We don't know what it is. How are we going to detect it, right? And those invisible physical structures that affect us, or that are all around us all the time, and these kind of invisible social and political and psychological, emotional structures. And when you get these people together, and instead, hopefully, through the discussions and the collaborations, and which take whatever form they might do, you open up a new space where new ideas can come in. And those are obviously the more interesting collaborations for me. And so, I mean, it would be great if Liam were here. It'd be great to have a conversation with him too. But I'll have to call him and talk to him about his slideshow. Do you mean, have I ever seen an artist-scientist collaboration that ended up like causing the scientist to make a new discovery? Yeah. Yeah. Ah, yes. Well, maybe going backwards first. So the thing that we get from the image of the black hole is more knowledge about that our models, our simulation of what happens around a black hole was more or less correct. So it's almost like a confirmation more than anything, because we had simulated what the hot gas around black holes should look like, and this more or less demonstrated that was pretty right. So you get something immediately scientifically from that, because it's confirmation that you should keep going, and that you should use this ability to see around black holes to better effect and do more of them, and really increase your knowledge of in that case general relativity. But what happens when, have I seen an example of some kind of concrete example I can point to where a scientist was improved by a collaboration with an artist? I think that I am an example, because every time I collaborate with artists, I end up with new perspectives on my work. But again, these I can only tell you anecdotally, because I can't point to something. It's like I went and did my programming better, and I increased my speed 10% or something like that. That's not what happens, right? What it does is it reminds the scientist that what they do is they're not doing it just for some selfish reason. They're doing it because the research we do really is trying to address large, big questions, large philosophical, almost philosophical questions. And because it's far too easy in our field, maybe other people in this room would disagree with me if they're also in this field, but it's really easy in the field, like as it is with any large field, to kind of get in a tunnel vision, to kind of get in one particular way of thinking about what you do. And I would advocate that almost all scientists get a chance to interact with an artist who to try to explain why it is that you do why we do what we do, to a mindset that would come at it with totally different questions. So when I collaborate with an artist, I end up having a sort of dialogue that goes in so wild ways that I could never have predicted, and I love that. I adore new wild ways. Maybe not everybody, every scientist would like that, right? But I think that it does end up invigorating your attitude toward your research, and it to a certain extent it could help remind you to keep going and keep doing what you do. Most of the people at CERN that I know that have interacted with artists have ended up with either, no one has come away saying it's like, oh, that was the worst thing I ever did, waste of time. It's mostly, it's either like, oh yeah, that was fun, or it was like, it was okay. But the fact that happens, the fact that we have that as a pursuit, the fact that scientists and artists can still have these conversations, to me demonstrates that we as a society still value differing perspectives on the same research, and it can end up with this kind of long tail effect. So I'm not sure I could point to one particular example. It's like, yes, Jane interacted with this artist and she ended up a 10% better physicist. But I can say that Jane interacting with an artist ended up slightly subtly changing her perspective on what it is that she did. And when she's then, for example, talking to some students, or talking to she's tasked with teaching an introductory physics class for art students, something that I've had to do when I was a grad student. You end up recognizing that people coming from different perspectives, their attitudes toward your research are totally valid, and this is a human being that is just as awesome as you are, and their perspective needs to be, you need to somehow connect with them directly, rather than just giving whatever kind of thing that you think is the right idea and then saying, no, you're wrong if you don't understand it. Yeah. There was another part of the question in there.
Right, yeah, no, go ahead.
So what was it again about the math? I'm sorry.
No, I was wondering, could it be that this is not a very big system, or it has problems within itself?
Yeah. So the thing about math is that it is a really interesting idea. It's a really interesting set of discussions, and I think that we could, depending on how much time you have, we can go for a very long time on this concept. Because again, what you're asking is super profound, and it's something that a lot of smart people, much smarter than I have thought about. Because really, what math is, I mean, a lot of people that don't go into physics and math, they get a sense that mathematics is like numbers and multiplication and like long division and calculus and stuff. And that's not really what math is. It's not you getting a homework assignment that has these really hard derivatives you're supposed to do. Math at its core, when you get to the really high level math, is about relationships between forms, relationships between quantities, and almost like abstract, being able to close your eyes and visualize things that are rather abstract things and see how the relationships work amongst themselves. So in that sense, mathematics, the ability to understand mathematics, is spatial and physical. And so the best mathematicians are the ones who can think in an abstract way, but still kind of spatially, if that makes any sense. I did a double major in physics and math, and so I still have a bit of a kind of a mathy dedication to some things. And I know that the underpinnings of what we use for both of these realms of math in general relativity and then in the realm of the small, quantum mechanics, they're really both reliable, and there's really no reason to think that they're wrong. And there's really no reason to think that there's really no reason to think that there should not be a coherent framework between both of them at some point, some mathematical way to connect them. And it's honestly, so I mentioned that the first level of putting these two things together gives you nonsense answers. But in fact, people for a long time have been coming up with ways to get them to play together just nicely. And you can do this, except that the current ways that this works somewhat nicely, there's no way for us to test them right now, or it ends up with other predictions that don't match our reality. So for example, you can postulate that space, in fact, has more than 3 dimensions. So you could postulate that there's not just 3 dimensions of space, but in fact other dimensions of space that may be everywhere around us, but curled up into a tiny little point or a circle or like a more complicated shape. And we've missed these before because they're so tightly curled up. And this is a way that you could help explain how these two things come together. But the length at which they're curled up seems to be much, much smaller than what we can possibly detect. And it's a straightforward way of adding some stuff into the mathematics of both the realms that ends up making them work together. So I don't think there's a reason to think that they shouldn't work together, if that's enough double negatives in one sentence. But I think the other question, I don't really know if having, say, mathematicians work with artists would help the math. Again, I think it might help the artist more than it would help the math. As we know from some of my other friends who really have done fascinating work where they have interrogated our assumptions behind what mathematics is and the way that we use it in both science and also everyday life. Like my friend Andrea Galvani, and he does some really fascinating installations where he took some kind of basic thermodynamics equations and he put them into white neon sculptures, like installations on a wall, and then he had kind of like a dance piece that went on in the same way. And he's kind of asking the question is like, we show these symbols, and these symbols mean something to a certain subset of society, but do the symbols themselves have power outside of their codification of some kind of physical rule? And then that physical rule in this case is writ large in the sky, in this installation, and then you have some other kind of physical form, human bodies going around underneath it. So I think that's kind of an interesting thing to do, because the kind of behind the scenes thing of all of this is a really, really important question that I've never really been able to answer for myself, which is mathematics a language? Is it something that humans invented to describe the physical world, or was mathematics discovered by humans? And is our universe secretly, behind the scenes, at its basis, a mathematical object? Because you might think that, sometimes you go one way or the other. Imagine, a little girl that has a ball, like a toddler. She throws the ball up in the air, and then it comes down. She does it again, and it happens again. And she knows intuitively after a few times the way it behaves as it goes up and down. The toddler doesn't need calculus to do that, right? She knows that there's a physical phenomenon where the ball goes up and down. And if she wanted to, she could describe it with calculus. But she doesn't need to know calculus to do that. So in that sense, the physical world comes first. Physical reality is what we experience. And then we invented mathematics as a tool, as a language, to describe the physical world around us. But in the other way, it's almost shocking sometimes how precisely the physical world follows certain kinds of mathematics, kind of related to this standard model thing, right? It's like, it's really shockingly weird how well the universe decides to, for some reason, follow these types of mathematical objects we can write down. And it starts to make you think, it's like, why would it bother to follow, why should I be able to describe the quantum field theory so precisely with this mathematics? Why should I be able to have this thing spit out almost exactly where these things called the Z and W bosons should be hiding? Why should all these things just sort of work out so precisely? And it makes you start to think, is our universe secretly behind the scenes a mathematical object that our universe instantiates these mathematical objects into physical forms? And that, of course, is related to one of my other obsessions, right? Which is that if that's true, if mathematics was discovered by humans, if mathematics is really the true underpinning of nature, and we discovered it, then why can I then conceptualize some mathematical objects that our universe seems to have no use for at all? Why would that be? I can envision in my head something called an 11-dimensional Calabi-Yau manifold. Okay, I can't envision it, but I can write it down. I can in some way conceptualize this mathematical object. I've never seen one of these in my life at all. I've never seen our universe seem to use it at all. So does that mean that if the true nature of reality, whatever that means, is mathematical in nature, for some reason our universe seemed to take a few of these mathematical objects and map them onto physical reality and then ignored the other ones? And does that mean the other ones are being used in other universes, perhaps? Again, it's total speculation, right? But these are the types of questions that you end up asking yourself when you're staring up at the sky in Utah.
No, I think that's all we have time for this evening. Of course, discussions can go on somewhere else, but for tonight, thank you, Dr. James Beacham, and thank you all for being here.